In the last video, we have talked about Fourier series, and in this video, we will continue on the properties of the Fourier series. Let's start with the extension of Fourier series. Remember, we talk about Fourier series. We define Fourier series in the closed interval negative pi to pi. But sometimes we need to extend it to the real line. So how can we do so? Well, the idea is very simple. The left-hand side here is a graph of a Fourier series which is restricted to the interval negative pi to pi. How can we extend it? Well, we can just repeat this pattern over the real line. But there's one issue. We cannot include this point when we repeat the pattern because the function value right here and right here are not the same. So if we attempt to define the function here, we should eliminate either this point or this point. And in my context, I would just eliminate the point in the negative pi, and therefore we will not have two different values at the same input. Well, and such extension is continuous if and only if f negative pi is equal to f pi, because f negative pi equal to f pi means that these points will be connected together after we extend the Fourier series. Well, let's start with some notations about the Fourier series of f. Suppose phi is a Fourier series of f. We notate it by f snake phi. But you may wonder why I don't write equal here. In fact, there are some examples where the Fourier series do not converge to f. We study the first simple example. The first example is fx equal to x, the identity transformation with x defined on the closed interval negative pi to pi. So I will leave it as an exercise to prove that f has a Fourier series 2 times negative 1 to the n plus 1 power over n times sine nx, and we sum n from 1 to infinity. So if you have done this exercise, you may find something. You find that phi of pi should be 0, but obviously f pi is equal to pi. So there's one point these two functions do not match, and therefore we claim that the function itself is not equal to the Fourier series. And therefore we do not write equal sign here. Next, I'm going to introduce some notation which is important in analysis. Well, given a sequence xn, we say that xn is equal to big O n to the s power if there exists some c in the real number such that the absolute value of xn is more than or equal to c times n to the s. And we say that xn is equal to small o n s if xn times n to the negative s power tends to 0 as n tends to infinity. So using this notation, remember that our Fourier series for fx equal to x is like this. And so we claim that the Fourier coefficient of fx equal to x is big O n to the negative 1. And remember, what does it mean? It means that the function here, it has the coefficient smaller than or equal to c to the n negative 1. And what is this? This is a very famous series called the harmonic series, right? And we know that the harmonic series converge. So the convergence of this series is questionable. We cannot determine whether this series will converge. So what can we do? And this is the motivation of our question. When will the Fourier series converge? Or when will the Fourier series converge to the function itself? And in fact, there is a convergence criterion, which states that the Fourier series of a continuous 2-pi periodic function which is C1 piecewise converges to the function uniformly, and I will prove it later. Well, there is something I haven't defined here. What is C1 piecewise function? Well, a function that is C1 piecewise on the interval negative pi to pi means that there exists a partition ij on I such that there are C1 function fj equal to f on the interval ij, and we subtract aj and aj plus 1, and where ij is the closed interval aj and aj plus 1. So what is this? This is just the closed open interval aj plus 1, right? So here's an example of a C1 piecewise function. Here there is a function that is made up of three C1 functions on three different partitions, and clearly these three are C1 functions, and so we called f a C1 piecewise function. And this is the end of the video about the properties of the Fourier series, and we will continue in the next video.